China's Tiangong space station has achieved a groundbreaking world record, heating tungsten alloy to over 3,100 degrees Celsius, which is nearly half the sun's surface temperature. This was made possible through a container-free experiment in microgravity, capturing pure data never seen before. In this video, we'll explore how it was done, why it matters, and what it means for the future of exploration. China's Tiangong space station recently achieved a milestone that really pushes the limits of material science. Scientists managed to heat a tungsten alloy to more than 3,100 degrees Celsius, setting a world record for high-temperature experiments in orbit. Tungsten is already famous for having the highest melting point among metals, around 3,412 degrees Celsius, and the ability to take it so close to its natural threshold in space demonstrates a unique level of precision. What makes this breakthrough stand out is the fact that it was carried out using the container-free material science laboratory cabinet inside the Tianhe core module. For more than 4 years, this facility has hosted experiments on tungsten, niobium, and other alloys to study how they behave under extreme temperatures. The aim has been to develop stronger, cleaner materials capable of supporting advanced technology in space and on Earth. Heating metals to such extremes on Earth has always posed challenges. When molten, metals tend to cling to containers or separate into layers due to gravity. This contaminates results and prevents scientists from capturing accurate measurements of an alloy's true characteristics. By taking the experiment to orbit, researchers were able to bypass these obstacles and observe the material in its pure state. This record is not just about hitting a new number, it represents the ability to push experiments beyond Earth's limits. With each degree achieved, Tiangong demonstrates that it is not only a space station but also a frontier laboratory dedicated to discoveries that could define the future of advanced materials. Understanding how Tiangong pulled off this achievement requires a closer look at the methods used. The secret lies in microgravity, which provides an environment impossible to replicate on Earth. In orbit, molten metals do not sink, splash, or settle into layers. Instead, surface tension naturally shapes them into perfect spheres. This property provides a clean starting point for experiments free from the interference of gravity. Inside the material science laboratory cabinet, the alloy sample was not placed in any container. Instead, scientists used electrostatic levitation, a technique where carefully controlled electric fields suspend the sample in mid-air. This means the molten metal never touches another surface, eliminating contamination or chemical reactions that would occur in traditional containers. The setup ensured that the data gathered represented the alloy's true behavior. To heat the tungsten alloy, researchers employed a dual-wavelength laser system combining a semiconductor laser and a carbon dioxide laser. Together they produced a 300-watt power output, delivering the intense energy needed to melt tungsten alloy into a glowing liquid sphere. This system allowed scientists to maintain stability and precisely control temperature in real time, something no Earth-based experiment could achieve at such extremes. With this setup, researchers were able to observe how the alloy behaved at every stage, melting, flowing as a liquid, and crystallizing during cooling. This information, often called hardcore data, is incredibly valuable because it reveals the structural processes inside the material without distortion. The implications of Tiangong's tungsten alloy experiment go far beyond the laboratory. This success offers practical lessons that may shape technologies we depend on for both exploration and daily life. One immediate area of application is spacecraft protection. Vehicles returning to Earth must withstand temperatures of several thousand degrees as they pass through the atmosphere. Alloys tested in container-free experiments could become the foundation for next-generation heat shields, offering safer and more reliable performance. Another critical field is propulsion technology. Rocket engines operate at extreme heat levels, and their components must remain stable under continuous stress. By studying how tungsten alloys behave at over 3,100 degrees Celsius in space, researchers can design materials that form the backbone of more efficient and longer-lasting propulsion systems. This could improve mission reliability and expand opportunities for long-distance travel. The impact is not limited to aerospace. In nuclear energy and fusion research, engineers are constantly searching for materials that can endure extreme temperatures and radiation. The data collected aboard Tiangong could inform the development of alloys capable of functioning inside future reactors, a breakthrough that would benefit global energy innovation. Industries such as aviation and advanced manufacturing may also adopt these findings, applying heat-resistant alloys to create stronger and lighter components. Beyond the technical outcomes, Tiangong is demonstrating its role as a world-class orbital laboratory. This experiment is evidence that space stations can serve as platforms for groundbreaking research, not just as living quarters. This breakthrough aboard Tiangong is more than just a scientific record. It's a glimpse into how space can transform research. By heating tungsten alloy to over 3,100 degrees Celsius in a container-free environment, scientists unlocked pure data that Earth-based labs could never capture. If you enjoyed this video, don't forget to like, share, and subscribe for more updates on space exploration and scientific discoveries. And don't forget to leave a comment below. Thank you for watching, and see you next time.